Hello and welcome to today's lesson on everyday forces, which is section 4 in our information. For starters, when we talk about weight, weight is a gravitational force exerted on an object, and on Earth, it has a specific value just like every other place. But it is a vector quantity directed downwards towards the center of Earth. So we can't have weight up and weight left and weight right. It's always going to be down. The magnitude is going to be a scalar quantity, but because it involves an acceleration in a direction, it's going to be vector, which is always down. And then weight changes with location in the universe. So on Earth, a person might weigh 180 pounds. On the moon, they would only weigh 30 pounds. So to calculate weight and force are again essentially the same thing. So weight is mass times acceleration, or mass times gravity. And so your force due to gravity is going to be equal to your mass times your acceleration due to gravity. On Earth's surface, and this is at sea level specifically, your acceleration due to gravity, which we just call g, is going to equal to 9.81 meters per second squared. And we use that with our kinematics equations, our motion equations, and calculations there. But that is going to be your value of gravity on Earth. We assume sea level, and that is the value. The normal force. So when we're talking forces, the reason we don't fall to the middle of the Earth is because the surface of the Earth pushes upwards. And this force is called the normal force, which acts in a direction perpendicular to the surface. So if you're on a flat surface, it's directed straight up. If you're on a plane, as is the box down here, your normal force is at an angle perpendicular. So if we would draw a line here, maybe, this would make a right angle with the ramp. So the normal force is not always in the opposite direction of gravity exactly. So for example, gravity is always straight down. This normal force is not. It's at an angle. But in the absence of other forces, so if we're not pushing or pulling or changing the force on this box, your normal force is equal and opposite to the component of your gravitational force that's perpendicular to the surface. For example, this force down here, if we would change and make this here, your normal force is going to be equal to mass times the cosine of theta times gravity. So mg cosine theta is going to get you your component of gravity that is equal to your normal force. Opposite direction, but equal in magnitude. When we talk forces, an important one that we encounter here on Earth and pretty much everywhere else except for space is friction. There are two main kinds of friction we're going to talk about. The first one is called static. The second one is called kinetic. So static friction, when we think of static means not moving. So static is a force that resists the initial sliding motion. So the initiation of sliding motion between two surfaces that are in contact and at rest. So this is the big piece of static friction. It's got to be at rest. So for example, this orange juice container here is not moving. So right now it has static friction with the table it's sitting on because it is not moving and it doesn't want to move. And this is the friction that resists the motion. So when you start to push something, it's really hard to start moving because of this static friction. Your kinetic friction, on the other hand, is the force that opposes the movement of two surfaces that are in contact and are sliding. When they are sliding or in motion past one another, that is kinetic friction. So in this case, I have my hand pushing the milk jug or the orange juice container to the left, and because it's moving, this one I guess is moving. This one's got a force, so these two are against each other. This is still static. Because this has motion, this purple vector indicates motion. Because it's moving, this is now going to be a force here going this way, and your kinetic friction, your F sub k, is going in the opposite direction. An important thing to know and remember is your kinetic friction is always less than your static friction. Always less. that it's always harder to start something moving than to keep it moving. And that's true mathematically, that's true all the time. So kinetic is always less than static. If we look at free body diagrams, which we've done before, your force of friction always has to go parallel to your surface of contact. So if it's on a ramp, it's going up or down the ramp, parallel to the motion, parallel to the ramp. If it's on a flat surface, it's going in a straight line, horizontal to the ground. And then your force of kinetic friction is always in the opposite direction of motion. It's got to be parallel, and friction always goes opposite the direction of motion. Friction doesn't help you go faster, it always slows you down. With the direction of static friction, we think back to Newton's third law and the principle of equilibrium. So your frictional force must be in the direction that results in a net force of 0. So this last sentence, the frictional force must point in the direction that results in a net force of 0. That's kind of the big piece here. So again, if we would have a box, put a box on the ground here. If I'm pushing it this way, this is my force applied, called F sub A. Then I have a force, and if it's not moving, that means I have a force due to friction, an F sub S, static friction going this way to hold that box in place. And those arrows are equal in magnitude, opposite in direction. That is keeping your net force of 0. So I'm pushing one way, my friction is the opposite. If I would change and I would pull from this side, so if I would delete those and I would pull from this side, my friction would still be going this way because it's opposite the arrows. So friction always has to go opposite the way that motion is being attempted for static. When we talk about quantity, the way to figure out how much friction is there is we have what's called a coefficient of friction. And this allows us to determine what the force of friction is on an object, or what force is needed to surpass the amount of friction. And so your coefficient of kinetic friction, so this is indicated by the Greek letter mu. And so this is mu sub k, which is your coefficient of kinetic friction, is equal to your force of kinetic friction divided by your normal force. And again, your normal force is the opposite of gravity, so it's the same as the force due to gravity, which is equal to your mass times gravity. So if you take the mass of an object times gravity, we're going to get our normal force. And that's going to be here. That's right there. And so this is for kinetic friction, mu sub k, and force of kinetic. And then your static friction is mu sub s equals your max static friction divided by your normal force again. And this is how so this is a ratio. Your force of friction compared to your normal force is your ratio. And that's going to give us our mu value, which you will be given in a table in order to calculate forces due to friction. An example of such a table is here. So you will see different values. An important thing to understand here is that the bigger the number, the more friction you have. So for example, rubber on concrete has a value of static friction of 1, which means that your force due to friction is the same as the weight of the object. Okay, on the flip side, synovial joints in the body. So think of your movable joints in the body. They have a coefficient of static friction of 0.01. So 1/100th the value of the weight of those two joints, the weight of the objects there. That is a very low coefficient of friction, which means it can easily slide, which is what our synovial joints do. Think of your shoulder, your elbow, your hand, your knee. All of those are synovial joints that move. Teflon, think of your cooking utensils, 0.04, still rather small. Ice, 0.1. All those are really small. These others are rather large. So sliding glass on glass, a lot of resistance, 0.9. Again, something to pay attention to. On this left side is your coefficient of static friction. This is your coefficient of kinetic friction. In all cases, the bigger number is on the left because your static friction is always greater than your kinetic friction. The one exception, one outlier here, is your Teflon on Teflon. That's the same, but it is never, your kinetic is never greater than your static. Static always has to be at least equal to, if not greater than, in most cases greater than your static. Or static is greater than your kinetic, sorry. If we're talking air resistance is a form of friction. So this is air moving over an object. So think of when you're running, when you're riding a bike, what you feel hitting your chest, that is air. So if I'm a person standing here and I'm moving in this direction, the air is going to push in the opposite, which is why on windy days, for example, if you're running with the wind, you run really fast. You feel like you're running really fast. If you run against it, it's rather difficult. But this fluid provides a resistance to the object's motion, and that's what we get with air resistance. And so as we talk about falling objects, you have a situation for a falling object when the upward force of air resistance, I apologize for my writing in the middle, when my upward force of air resistance is equal to my downward force due to gravity, the net force is going to be 0, which means this object will no longer speed up. At this point, you have reached what is called terminal speed or terminal velocity for falling objects. So for example, when you go skydiving, there will come a time when you're falling. So if this person is skydiving without a parachute, there will come a time when you're falling that your force due to gravity and your force of air resistance are equal. And at that point, you will no longer be speeding up. You'll be at a constant velocity, constant speed downward. You won't feel like you're falling any faster because you're not. You're moving really fast, but your velocity will stay the same. Because these two forces are balanced, you're no longer speeding up. All right, and the last thing I would like to talk about is there are 4 fundamental forces in the universe. Every interaction you can think of will come back to one of these 4 forces. The first one is a strong nuclear force. The second is an electromagnetic force. Third is a weak nuclear force. And the last one is gravity. Value-wise, strong nuclear force, we would give it a value of 1. We'll compare everything to this. So if a strong nuclear force has a value of 1, we'll compare everything else to that. So if this is 1, our electromagnetic force is going to be 1 over 100. So your electromagnetic force is 100 times weaker than your strong nuclear force. Your weak nuclear force. Your weak nuclear force is going to be weaker than that, which has a value of 1 over 10 to the 6th. 1 over 10 to the 6th. So much weaker than this strong nuclear force. So this is your the force between protons that holds protons together. This is your proton-neutron force right here. It holds your protons and neutrons together. That holds all that. That's a glue holding positive charges together. It's a very strong force. Your electromagnetic is going to be your protons and electrons, or your electrons and electrons pushing against each other. So every push and pull you encounter, the reason that you don't melt into the chair that you're sitting on, the reason you don't fall into the floor, that is your electromagnetic force. So this is your electrons in your body repelling electrons elsewhere. Your weak nuclear force are all the subatomic particles involved in an atom, is what this encounters. And then we have gravity. Gravity, the thing that we're taught is super strong. Gravity has a value of 1 over 10 to the 38th. Super tiny force compared to the rest of these. But every interaction you encounter in the universe can be placed into one of these 4 fundamental force categories. And these are all field forces that nothing actually touches here. Nothing is in direct contact, they're all at a distance. That is the end of this video. In the next video, I will do some practice problems with friction, and we'll work through those kinds of questions. Thank you for watching, and enjoy the rest of your day.